It's there. It's on. We're in.
We're in.
Yeah.
Go ahead.
You've gotten a bit fuzzy, FYI.
Oh, wait, hold on. Let me adjust that. And you introduce us while I adjust that.
Hello, everybody. I haven't got my notes in front of me. What episode is this? This is episode 55, or index 055 of Undersampled Radio. Welcome. Pretty exciting show today, right, Graham?
That's right. We're here live and direct with a new guest, fascinating riddle, and some awesome news. So straight to it. What's happening in your world, Matt?
Well, my world's guess looking at these things that I've written down, it's looking pretty computery right now. Well, as usual, I suppose. But I bought a new external graphics card for my Mac. So it used to be, well, okay, it still is a little bit of a hassle, but it used to be quite a big hassle to get an external graphics card set up on a Mac. They didn't support that in the operating system, and some of the drivers weren't supported. But now it's a bit easier. I bought an Akitio Node Thunderbolt 3 enclosure, which basically takes care of the power requirements of the graphics card and the connections, the Thunderbolt interface, and a NVIDIA GTX 1080 Ti card, which is, I don't know, 3,500 GPU cores and 11 gigs of RAM. So it's quite a nice GPU for we're doing a lot of GPR simulation right now. So that's why I bought that, because some models take quite a long time to simulate. And essentially it makes things that you couldn't do, or that were highly impractical because they take very, very long time to run, it makes them practical, because the speed up is sort of 10 to 20 times depending on what kind of machine you were trying to run CPU. So that's pretty exciting. And relatedly, NVIDIA had an offer for their developer network recently. It may still be going on, actually. I should look for the link in a second and put it in the notes, just in case it is still going on, where you could pick up a Jetson TX1 developer kit for only $200. I think they're normally about $500, so it's a pretty good deal. What is a Jetson TX1 developer kit? Well, the Jetson cards are basically little NVIDIA Tegra processors with a CPU and a bit of RAM, and they're designed for embedding. So they're designed for kind of mobile deep learning stuff or mobile image segmentations, the sort of thing you might stick on a drone or on a vehicle or something like that. And the developer board or kit is basically this thing, the Tegra processor module stuck onto a developer board with breakouts and USB and power and all this kind of thing, and a cooling block. So potentially really fun. I haven't actually had a chance to play with it yet. I'm going to bring it along to the hackathon in Houston, assuming that goes ahead as planned, and see what people will do with it. Maybe you can put some deep learning on a geophone, or come up with some cunning drone application or something. Yeah, I don't know. Have you played with anything like that, Graham? Seems sort of up your alley.
Nope. I have not.
Okay.
All of I mean, I have, various whatever NVIDIA cards here in this room, but mostly I just spin up a GPU instance to do big jobs.
Yeah.
We were talking the other day about having GPU as a service, which would be kind of cool. The idea being you are running something on a CPU instance and you need some more power, and you just say something like, import GPU as a service, send to GPU as a service, run. And it would spin up a GPU for you and take care of all the details, and then you would just have fast computation.
Yeah.
Yeah.
Totally.
So
and there's always half a dozen ways of doing things, but I feel like a lot of developers either forget or just choose to ignore the fact that these things are actually quite tricky to set up, even when you half know what you're doing, at least the first time, and also the second time, because you've got to take notes the first time and you don't do it very often. And for kind of non-super geeky people, it's basically so difficult that it's a total roadblock. So even getting these external graphics cards set up is not particularly straightforward. And I feel like we need more things that just like break down
Press
all those
the
barriers.
button and go.
Yeah. I don't want, at the risk of going on and on, I did want to mention a couple of things because I think our guest Zoltan, who we'll meet in a second, will be quite interested in at least one of them. I just read about the publishing company O'Reilly, so I haven't totally figured out what they're up to, but I gather it's something to do with their books, have launched something, so they do a lot of computing books, launched something called launchbot.io. So launchbot.io, and it looks like being a clever way to manage Docker containers and launch notebooks sort of seamlessly and manage notebooks, Jupyter notebooks seamlessly using Docker. I had a quick play with it just now for about half an hour, and it didn't. I mean, I got a local notebook running, but what I want is, when I've got an awesome notebook and I want to share it, I just want to share it with one button, right? Have it appear on the web, not just so that someone can clone it, because obviously I can do that with GitHub, but so that they can actually run it and like away they go. Like that's what I want. One button, click.
What about Binder?
So Binder, mybinder.org did that almost, kind of. Like you could launch it from a GitHub repository with one click and it would run. It took a little bit of fiddly setup because it was also using Docker. So you had to write a Docker file and stuff like that. And a YAML file to define your environment if you wanted to use some libraries and so on. But then basically the mybinder.org, I can't remember who was running it, but obviously it was on a bit of a shoestring, and basically the whole thing just fell over eventually and it was never up. And I think to this day, mybinder.org servers just aren't working. But JupyterCon was last week, and Rowan Cockett, who we've had on the show at least once before, awesome geoscientist, programmer dude in Calgary, told me that Fernando Perez, who runs the Jupyter project, has funding to rescue mybinder.org, and there's already beta.mybinder.org is apparently up and running, and that's the beginning of the rescue process. So hopefully soon mybinder.org will work again. In the meantime, Azure Notebooks is actually quite good. And so I've been using Microsoft Azure Notebooks. They've now got a thing where you can give it any GitHub repository with notebooks in it. You just give it the URL to the GitHub repository, and it will instantiate an instance, and you can run your notebooks just like that. You do need, cool. Yeah, it is really cool. You need a Microsoft account, so you have to log in. Think certainly do to, you know, I'm pretty sure you do. Certainly last time I checked, you needed to be able to log in. I'm just logged in all the time, so I'm not totally sure. So that's one drawback. I'd like people not to have to log in like they didn't have to with mybinder. But yeah, anyway, check it out. It's pretty cool. And I've got one thing running, my X lines for the X lines of Python blog series that I do. My GitHub Agile Geoscience X lines repo has the Azure setup file in it if you want to see how to conda install and stuff to get your environment set up, because you probably want some other libraries other than just SciPy, NumPy. There you go.
Yep. Here I am having crashed one computer during that speech. So while I pull up my show notes, why don't you introduce our guest?
I'm so sorry. It's not supposed to be a speech. Don't call it a speech. I have a lot of stuff to share. Like I just, you know. Yeah, anyway, today we have Zoltan Sylvester with us on the show. And I'll just pause to mention that Zoltan's an internet friend. We met on Twitter, I think. And I've met him a couple times in person, once at APG in Houston. And I can't remember if it was the same trip or I think it was a different trip. We met at a really cool pub called the Petrol Station. I hope it's still there and not underwater or threatened in any way. It's a really nice pub that sells fantastic Scotch eggs. So is the Scotch egg tip for the week. And welcome, Zoltan.
Well, thanks for inviting me.
Yeah, sure.
Are you dry?
Here in Austin, it was fine. Like, I mean, there was one night when it was kind of rough, but nothing. Like everything is a small thing compared to Houston. So.
Good. Well, I'm glad to hear everything's okay over there, and we hope that everyone in Houston's doing okay. If not, check in on the Software Underground and tell us what's happening.
Yeah,
Zoltan,
I was just going to ask Zoltan because I lost track a little bit of what Zoltan was up to when he moved, like in the spring, I guess it was, over to Austin from Houston, where he was previously at Shell, if I'm getting the order of things correct. And now you're a professor at UT Austin. Is that what's going on?
So I'm a research scientist at the Bureau of Economic Geology, which is a research institute, and it's part of the UT Austin system.
Right.
And I actually was, I know it's confusing. I've been changing jobs quite a bit in the last few years. I used to be with Shell until 2014. And then I went to Chevron. I was with Chevron for 2.5 years, and then moved to Austin just in December last year.
Right. Yeah, Shell Chevron, not Chevron Shell. Right. So, and how's it going then in Austin? You must be fairly settled in now. I've seen you've been on some cool field trips.
Yes. So it's I'm still working on similar things that I used to work before, and the reason for that is I like doing that kind of stuff. But it's more. I have a lot more say in what projects I'm working on, and so it's a lot of time for focusing on researchy ideas and more freedom, little bit more freedom to define actually what you want to do and how you want to do it. We are basically a group of people here and called the Quantitative Classics Laboratory, and right. We are funded by an industry consortium, which is mostly oil companies.
Okay, and who are the folks that are kind of running that lab?
So Jake Kovold is the principal investigator, if you want, and he has a very similar background to mine. Sedimentologist, mostly focusing on deep water sedimentation. And then Pete Flagg is another research scientist. He's more fluvial / shallow marine oriented sedimentologist. He has done a lot of work in Alaska and does a lot of outcrop mapping and descriptions and just good old field work with some new techniques lately. And then we had Glenn Sharman, used to be a postdoc just until a month ago or so. He was with Conoco before. He's an excellent outcrop guy. He's also an excellent computer geek. Very quickly picked up Python, and he's doing, in general, he's a fantastic guy. Unfortunately, he left because he has started, in fact, assistant professor position in Arkansas.
Oh, okay.
Well, it sounds like you guys have an awesome group. What are you working on?
So one of the things I used to work on while in the industry was submarine channels. That was one of the main things, and I find especially sinuous channels or meandering channels, so fascinating that I just can't stop doing it. So I've been looking at just in general, how do you model meandering properly, and how do you build reservoir models once you have the meandering part figured out. Just recently, I went to a conference in Calgary. I think it was the 11th international conference on fluvial sedimentology, something like that. I might have not gotten that right, but anyway, it was like a big gathering of people who are working on fluvial geomorphology, fluvial sedimentology, stratigraphy. Really good conference. It was my first foray into fluvial subjects, and it was great. I learned a lot. I got some new ideas going, so I'm pretty excited about actually doing some work on fluvial systems.
Because you've been focused on deep water,
almost exclusively.
Right.
But the more I look, the more interesting it becomes. You know, like how far you can take the fluvial analogy into the deep water, and what are the differences, and you know, there's some divergence of opinions along those lines. Some people would argue that submarine channels are so fundamentally different from fluvial channels that there's almost no point of comparing them.
Right.
I'm more I'm a big fan of the idea that a lot of what we know about fluvial systems can be translated in one way or another into learnings about deep water channels.
So are you going to start modeling fluvial systems as well?
Yes, because I already started doing that, and I think the underlying bare bones, not algorithm but process, is essentially the same for highly sinuous systems. It's essentially an instability driven by the centrifugal force, and ultimately it's not that complicated. I think, depending on how far you want to go into the details. But
yeah, tell us a bit about the modeling. You know, we've seen. Well, I'll get to your blog in a minute, but you've got some cool outputs of sinuous channel models that run forward in time. How do you build those things? What are your inputs, and how does the workflow go?
Right. So I'm using Python for pretty much everything nowadays, and it's the core of the model is probably like half a page. It's essentially comes down to the idea that the migration rate of a sinuous channel, of a meandering channel, is a function of not just the local curvature, but the weighted sum of the upstream curvatures at every point. So it's just a summation of curvatures, a weighted sum of the curvatures upstream from the point where you are looking at, and that's basically, you multiply that by a constant, and you got the migration rate. And if you try to run the program with just using just the local curvature, like you would, for example, if you want to calculate the force acting on a car in a curve, of course, using the local curvature is fine. Sure. But if you do that for a river, the model is not going to work. It's unstable.
Right, because the state of the system is determined sort of in a time. You know, if you take like a volume slug, like the flux through one section of channel is affected by the upstream curvatures, because there's sort of like a fluid history there.
Right, and the river doesn't. I have to be careful what I say because not it's not that easy actually to describe it, or maybe I just don't know. But the river doesn't know, of course, that there is a bend coming up. So
Right.
so it's going to run the high velocity core is going to, with a delay, it's going to run into the outer bank, and that's where the erosion happens. If you only have the same radius of curvature but only a little turn, that's going to have a smaller effect
Right.
than having the curve is wrapping all around the circle, the same circle. Then that's going to have the river is going to go really hard into the outer bank, and then the erosion, therefore the migration rate, is going to be larger.
This is pretty fascinating. I've never thought about this before. In case audience, you're not following the whole conversation, we're talking about starting from basically a flat piece of earth, running volume flow of some fluid across that, and as you introduce curvature into the system, the stream or the channel will meander according to, as we've just learned, upstream curvature properties. How far, I guess it's subjective according to velocities and things, but how far back in the spatial sense do you see the effects of curvatures?
It's basically, it's not a long distance. It's on the scale of a few channel widths upstream.
Oh, is that all? Okay.
Yes, but that matters because what happens is that if you are driving, the biggest force on the car is going to be at the point of highest curvature of the road.
Sure.
In a river, the point of highest erosion is going to be delayed downstream from the point of highest curvature because you are summing curvature. So the maximum migration actually is going to happen a little bit, again, maybe a couple of channel widths downstream from the apex of the bend. And again, if you don't put that into the algorithm, then it doesn't work. And whereas if you do, then you get these beautiful part of the reason I'm interested in this is that it's just patterns are so beautiful that
it is amazing.
Art and science.
Again, I know nothing about it. I saw the outputs on your blog and on Twitter. He's got these amazing 4D models of channel incision into a volume. It's really very beautiful. So then the next part of the modeling must be to derive reservoir characteristics based on the channels, right? Are you doing that work too?
Yes. So the idea is that if obviously in an industry setting you are interested in putting porosity permeability, well, let me step back just a step. So what I talked about so far is just giving you a skeleton of a channel system. If you want, you only have the center lines. You have to build a 3D model out of that. So there are a few steps there that we do, and that's probably the most how should I call it? It's a little bit like using Adobe Illustrator to fill in the details. So I think there's room for improvement there, but obviously I don't do that in Illustrator, I do that in Python, but we are wrapping these surfaces around those skeletons. And then the next step is to fill them with properties. And essentially the idea is to use grain size, some kind of distribution of grain size as a function of the model, locations in the model, to distribute porosity and permeability. And when I say proxy for grain size. It can be something as simple as coarse at the bottom of the channel and finer as you go higher up above the channel. And especially in deep marine settings, this is a pretty strong. We found before when I was still at Shell, we did quite a bit of work on this, and we found that there is a lot of dependence on grain size, on how high up in the current you are, how high up in the channel you are. It finds really quickly.
Do you think there's any possibility of being able to model these systems with sort of just with pure physics? Because you're sort of modeling there's some geometric constraints that you've introduced, and then you've got to kind of look at distributions from the field and kind of map those into the geometry that you create. But what about just sort of go straight to the grain size distribution by distributing grains?
Yes. So the answer is yes. And there are people and groups, research groups who are doing that as we speak. I think it's fantastic stuff and super interesting.
Fantastic, awesome, or fantastic like a fantasy?
Well, I think it's fantastic, like for real. But I think that the challenge is the if you want to build like it basically takes days or weeks to run one of these models.
Sure.
And then you have a humongous amount of detail, but how do you actually use it in aside from having this beautiful model which you can slice and dice and learn from it, which is I think that's one of the most useful aspects of this, that it's like a digital sandbox, and you can learn a lot just by running these numerical experiments. I think when it comes to actually applying it in reservoir modeling, that's hard.
Because the timeline is too long?
Partly because computationally it's very expensive, and partly because how do you the usual problems, and I have with my models I have actually similar problems. How do you condition it to wells, and do you use it as a training image and then use multi-point statistics? All these issues come to surface. So I think it's definitely I think it has its place both in academia and industry. It's an interesting. It's probably the future, but I also think that simpler models have also their advantages, and we can still learn quite a bit from simple models. I think Chris Pello made that point, and probably others as well, that if you build a model that is exactly as complicated as real life, then you are back to trying to understand your model because it's so complicated, just like nature. So models by definition have to be simpler than the system you are trying to model. Maybe I'm stating the obvious here, but
yeah, no, I mean, I suppose it's sort of obvious in hindsight, but I mean, the temptation with modeling is to keep adding parameters, right? Until you've taken care of all of the things that you perceive as variables, but then you've lost. It's very difficult to keep track. Well, computation becomes very expensive, like you say, so you can't explore as much of the kind of parameter space because it just takes too long. So that's one nice thing about simple models, is you can run a billion of them in the same time that you can run one complex one. But you also lose sight of the interaction between the different dimensions, right?
Yes.
And,
I'm finding that having 5 input parameters
right.
is plenty. I have a hard time keeping track and doing conditioning and
right.
Yes.
But I do wonder if there's a smart way to kind of get the best of both worlds somehow, and you know, I don't know, somehow have a modeling strategy that exploits both types of model simultaneously?
Yeah, I think one of the ways I think you can combine the two is that, for example, if I build a nice looking channel surface in maybe in a way that is not, it kind of resembles what you see on the seafloor or in Google Earth, but it's not, there's not a whole lot of physics behind it. And then you run one of these very sophisticated models on that surface, right, and see where sand is going and where mud is going, and then analyze the results and try to distill them into simpler rules for distributing the sediment in your model.
Right.
I think those kinds of links are a good way to combine the two types of models.
So you do the things that require the kind of large scale multi-channel field scale things cheaply, and you do the kind of core scale to you know, prospect scale stuff expensively, and then you sort of merge them in scale space.
Yes.
Yeah. I like that.
Conditional optimization.
Right. Yeah. Sort of a
boundary conditioning or something.
Because then you've also got, do you guys do any physical modeling? Because, you know, that's another avenue that people go down instead of numerical stuff, is they'll just build a tank and start distributing sediment around that. Is that something that goes on at UT or BEG?
There's definitely a lot of that going on at UT. At the Department of Geosciences, David Morig and Wonsak Kim have a fairly big, not fairly, it's a big facility here we are on the Pickle Research Campus, and the Flume tanks that they are using are just across the street from here. So we do have plans to work with them on physical modeling. So far, I haven't done much of that.
Yeah, again, it would be really interesting to see a sort of, well, as a total outsider, my perception is that there's a lot of stuff happens in the Flume tanks that then gets computerized somehow. But is anybody also going the other way down that street and sort of, again, you could almost build the container with your less expensive modeling, geometric modeling, if you like, and then try and replicate that somehow in the Flume tank and do the tricky part, but on a different scale, and then bring that back in. It feels like with sort of 3D printing and some of these awesome Flume tank geometry things they have these days, you could do that.
To some degree, that has already happened. There are people have built models of built a channel surface, like a submarine channel surface, and of course they did this for rivers as well. And then you would let loose a turbidity current in a predefined channel and see what happens in the bends. Where do you get more overflow and those kind of problems. One of the difficult parts in that is that it's hard to get a proper scaling between the channel and the turbidity current, and ideally you would run these experiments so that the channels are self-forming, and then they are, you know that they are the channels that those turbidity currents would like to create. It's not something superimposed, and then you don't really know whether you have an equilibrium or quasi-equilibrium condition or not.
Yeah, I see what you're saying. Yeah, I just I wonder a little bit if this might be a horrible idea, but if you can somehow bring physical modeling into the computational fold, I'm imagining a sort of API for your Flume tank, where it's like your modeling suggests that there's a lot of uncertainty around a particular parameter, so it sets up an experiment in the Flume tank to determine what happens there, rather than running an expensive numerical model.
Right.
So this is ridiculous, but yeah, you get what I'm saying.
I guess, I mean, you know, the classic way of using Flume tank experiments is I guess one of the classic ways is that I keep talking about turbidity currents because that's what I know about. But you would have a numerical model for a turbidity current, and then you would run some simple Flume experiments, obviously at fairly small scale, and then you would calibrate and validate your model so that it reproduces, given the same initial and boundary conditions as in the Flume experiment, do I get the same results for velocity profiles, for sediment deposition, sediment concentration, and so on. And then you say, okay, I'm able to match these experiments, and then I have some confidence that I can run the model at a larger scale, much larger scale, which is impossible to model in the Flume tank. I guess that's the one of the key ideas behind Flume tank modeling.
Tell us a bit about decompaction modeling.
Yeah, so that's that was a little bit of a little side project that I became interested a while ago, and the reason I became interested is that we spent a lot of time looking at outcrop analogs for reservoirs, and that work basically comes down to put it in a very simple way. It's a mapping of where sand is and where mud is, and so we have these maps of outcrops, and we never say never, but usually we don't think about how this would look like if it was decompacted. And I think the answer to that question is it would look the same, and it would look pretty boring if you have a stratigraphy that is close to layer cake, because then you are just changing the thicknesses of the layers, but nothing interesting happens. It becomes much more interesting when you have like interfingering of mud and sand, and then it becomes pretty interesting. So what I was trying to do is to decompact these outcrop panels or maps and see how the architecture changes and so on.
Yeah, it's nice nice to be able to do that programmatically too, because I feel like I've seen people trying to do that on sort of a 2D section, but in a way it doesn't make all that much sense to just decompact everything, because there was a sort of progressive, there's a time element, right? You have to do it in the time dimension as well.
Yeah, initially I started doing just that, basically saying, oh, I just multiply every mud layer becomes, this much thicker, and every sand layer becomes that much thicker. But that doesn't work. Like, no. I mean, you get something, but it's almost certainly incorrect. And yeah, you have to do it iteratively, and yes, you have to decompact in time steps.
Yeah, so it's a really nice application. Now, did that, when I read that post originally, I think you hadn't published the code yet, and I haven't, Zoltan's GitHub repo, everyone, is Z Sylvester. His Twitter handle, by the way, is ZZ Sylvester. But did you publish the decompaction stuff?
Part of it, yes. Basically the groundwork, if you want, the 1D decompaction.
Right. Okay.
It's out there. I have a Jupyter notebook.
Nice.
I did not include the part where, which I think is the easier part, where you take a 2D image and apply the same codes to every column, and then basically you get what you want
Yeah.
that way. In the meantime, I discovered that somebody did a much more sophisticated decompaction Python notebook,
Really?
which I haven't had time yet to play with it, but it looks very nice. If you go to my blog, it's and this decompaction post, they are in the comments. You will find that
Okay.
that work linked to Jan Zaretsky's work. He's at Saudi Aramco.
Yeah.
These
right.
are all linked in the show notes if anyone's looking for that.
Yeah, it's kind of like at first you sort of think, oh, you know, rats, if only I'd known about that or whatever. But actually, you need, you know, I mean, I imagine in your case, you said it was a side project. You're doing it as a sort of learning and exploration exercise, right? It's a journey of discovery of not just the code, but also the natural side of it, the natural science. And you know, so this is, I think to a lot, sometimes to non-programmers, it's like, why are there so many packages for things? Why has this person replicated all this work? Well, it's because that's how we think, right?
Yeah,
when you're a computational scientist, it's like you think in code, and so you need to express it.
And I find that I don't really understand something until I try to. It may be a super simplistic way, but if I try to code it up, then I really start to understand what's going on.
Yeah, it's just like when you try and write about something, or when you try and teach something to someone else. When you write code about it, you suddenly realize, oh, I actually don't know how that thing works, right? And now suddenly I need to know. So it totally forces you to figure stuff out. And you know, I'd sort of stopped using things like textbooks much at all until I started coding, and then it's suddenly you realize you actually need all these fundamental equations all the time. And I started buying textbooks again so that I've got these things to refer to, because they're often not in Wikipedia or wherever else you might go. Yeah, that's really cool. So do check out Zoltan's blog if you haven't seen it. It's called Hindered Settling. I think I've got the URL somewhere. It's on Blogger, right? So have you got a URL for it?
It's WordPress. It's hinderedsettling.com. Yeah.
Also linked in the notes.
Okay, hinderedsettling.com. There we go. Yeah, I must be looking at some old site there. Yeah, so do check it out. It's, you know, one of those, especially if you're getting into coding, especially with Python. It's a good one to know about, because Zoltan often publishes these side projects and code projects where he's actually exploring something numerically. So definitely worth knowing about.
Oh, Matt, are you ready to do the riddle?
Wait, why do I need to be ready?
Because you have to correct me when I say something.
Oh, I see. I'm ready to listen. Yeah, sure.
Okay, I want to introduce this section by highlighting that none of our listeners submitted a correct answer, which is the first time that's happened, right?
Okay, yeah, wow. Did Ari not submit anything?
No.
Oh, okay. Well,
he only submits if he has every
practiced.
possible correct solution.
With a full notebook and
it's amazing.
Tests and everything.
All right, so here's the question. I guess I have to read the whole question again. I apologize. I'm going to do this as quickly as possible, and then we'll get back to the rest of the show. Okay, so here's the question. You have N users in a Petrel project, and each one of them has interpreted one seismic horizon. The horizon files are indicative of the author's index. So for example, author 1's horizon would be 1.horizon or whatever. Okay, so that means that all of the horizon files exist in the set 1 to N inclusive. So last month, the project was corrupted, and the only backup is stored on tape reels in the data room. There's one horizon per tape, and the tapes are randomly just thrown into this room. Okay, so the users, each of the users gets to enter the tape room and examine n/2 of the tapes only, gets to read n/2 files only. Then they have to put the tapes back in the order that they found them. And they are not allowed to speak with the other users during their examination phase. However, they are allowed to speak beforehand, before any of the examination begins. Let's say they go out to the bar the night before, have a beer, and discuss the strategy which they're going to use to all find their respective interpreted horizons. Because if each one of them can't find their individual horizons, they'll all be fired. But if every single one of them recovers their horizon, they will all be allowed to keep their jobs. So the question is...
This is actually how most oil and gas companies operate, right?
I didn't say...
True story.
I didn't say your little quip about the file name. Do you want me to say this is one of Matt's favorite jokes, okay? You see that? I wrote that in there for you. I said... Oh. The name of the horizon is dsand_pre-stack_final_January 2017 _final_x, where x is the author's number. Anyway, the question is, at the strategy meeting the night before, what's the best strategy they can come up with? And more importantly, what's the probability of them all keeping their jobs using that strategy? Okay, so, there's two reasons we could have received no correct answers. One is our audience is quite small. Two is the solution is completely non-intuitive, at least to me. And I find it fascinating. So here it goes. All right, so if each user were to randomly select tapes and read them, they would only have what probability of finding their horizon then? There's n tapes, they only get to examine n/2.
Half.
Half. However, there are n users. So you have to apply that 50% probability n times. So the probability of n users all randomly guessing their correct horizon thingamajig is 1/2 to the n.
Wait, this, maybe I asked this last time. I don't think I did. Are they allowed to communicate with each other after they've done their inspection? Okay.
No.
That's annoying.
Yep. So
what kind of company is this?
1/2 to the n.
Who is the seismic data manager at this place?
1/2 to the n rapidly becomes you're not going to keep your job.
Right.
Okay. So are they screwed? The answer is no. Not necessarily. So here's the best strategy. Each user, upon entering the tape room, reads tape index X, which is the author's number. All right, so author 1 will first read tape 1. Now, when they read tape number 1, they then will read the next tape corresponding to the horizon number on the tape. So, and they'll keep doing that, okay, for all of their n/2 guesses. So, for example, if user 1 goes in there, they'll read tape 1. If tape 1 contains file 1, boop, you're done, because they found their file. However, if tape 1 contains file 4, they'll then read tape 4. Mm-hmm. If tape 4 contains file 23, they'll then read tape 23, okay, and on and on and on until, or unless, they find horizon number 1. So what you're actually trying to find here is what you're interested in is the longest tape reading cycle length that can result in a user finding her horizon file. And that in this case is n/2. Okay, because that's the number of guesses or choices they get. More specifically, we're looking for all the possible cycle lengths less than or equal to the number of random guesses from the set. The number of outcomes for a random permutation of tapes to have at most one cycle length greater than n/2 is n choose q, where Q is the desired cycle length, which in this case would be n/2. So users choose users over 2. Okay, so therefore, the probability that all n users find their files is equal to the probability that a random permutation of the tapes provides no cycles longer than n/2. So like out of all the permutations you could have with n tapes, you're only interested in the n/2 cases. Okay. Combinatorially speaking, this probability is, here's the answer finally, I apologize, equal to 1 minus quantity harmonic number n minus harmonic number n/2. Okay? Do I need to review before I tell you the weird part? Should I review what a harmonic number is?
Yeah, I don't know what's a harmonic number.
It's the nth harmonic number is the sum of the reciprocals of the first n natural numbers. So harmonic number n is 1/1 plus 1/2 plus 1/3.
Okay.
Okay. So, okay, let me just say it again. Okay, so 1 minus quantity, harmonic n minus harmonic n.
What do you mean when you say quantity like that? What does that mean?
Okay, let me go backwards. Harmonic number n minus harmonic number n/2.
Yeah.
That is a quantity.
Okay.
So you want 1 minus that quantity.
Oh, I see. You're using that as
parentheses.
A kind of grouping. Is that's a math thing, is it? I've never heard that before.
It's a
or is this a gram thing?
I haven't heard it either.
No, it's a math thing. You can find it on at least Urban Dictionary.
I'm going to start using that a lot.
Do.
It's very geeky.
Okay, so
whenever I want someone not quite to know what I'm talking about, I'm going to use it.
If you talk to a math person, they will know what you're talking about. Okay, listen. So here's the weird part. That answer.
It gets weirder. Okay.
Yeah. Asymptotically decreases to 30% as n increases.
Wait.
Yeah.
As n increases,
yes,
it decreases to 30%.
Yes.
0.3 exactly.
No, in fact, not exactly 0.3.
Okay. What then? 0.3.
I don't know, some very small number over 30%. So if you have 100 users, it's you're basically at 30%, and as you increase, you get even closer to that whatever number.
That's really strange.
Yeah.
So is this week's riddle me this to explain that?
Oh. Yeah.
In an intuitive way.
Whatever. Yes. Yeah. It's I mean, you can kind of see the cyclic permutation part of the riddle, right? So you've got cycles that the users take cycles through the total input space or whatever. Mm. There's a certain number of those which work, which is n/2 or less, and a certain number of those which don't work, which is greater than n/2. So as you stretch out that n thing,
right, that proportion settles.
Right. Okay.
Yeah. Right. Okay. It feels almost like it feels almost like you could solve that problem in graph theory.
If you solve that problem in graph theory and submit it as a Jupyter notebook,
I don't know what I'm talking about, but the way you're talking about cycles and things, it sounds like something you could almost do. But it's combinatorics, so it's what is that, number theory?
Yeah.
I don't know what I'm talking about. It feels like a very esoteric problem, but it is a fascinating result.
Yeah, it's kind of shocking to me, but maybe I just haven't gotten my head around it. The quantity result is very surprising. Hey, Zoltan, what are you reading at the moment?
I'm reading a fun book. Like, in other words, I'm reading it for fun. It's called The Angry Chef, and I found this writer slash chef who calls himself The Angry Chef, I think on Facebook or something like that, and he's really funny. And
is it a recipe book? It doesn't look like
no, not really. It's more of a sometimes he does get really angry about like pseudo-scientific stuff about food, things, all kinds of diets. He's not a big fan of diets, and things like fat is bad for you or sugar is bad for you, and end of discussion. These extreme points of view. He's scientifically deconstructing these things, and that's not a good word, but anyway, and he's also funny at the same time, and he has a lot of fun with Gwyneth Paltrow and her goop.com, and so it's recommended. There's quite a bit of science in it, actually. He talks to people who write peer-reviewed publications on sugar and
interesting
all kinds of food.
Yeah, that's kind of neat. It seems like that whole area is really rife with pseudoscience and fads, obviously. And exercise science, I would say, is fairly close behind with, but it's always quite amusing seeing all the one of the current things seems to be, I noticed we were watching quite a lot of the IAAF World Championships because it was quite nicely live streamed by the IAAF on YouTube. So it was quite easy to watch it. And what is it with these sort of weird bandages and sort of tape that athletes are wearing these days?
Yes.
Really do anything? I just thought your skin was elastic enough that all it does is stretch a bit of your skin.
Yeah.
I don't know what they're up to.
Let's try it. Let's put a big M on your back next time you go for a run and see if you can. Matt, what are you reading?
Well, I'm reading a sporty book at the moment, a kind of a memoir by an athlete called Kylian Jornet, who's well, he calls himself a mountaineer primarily. I sort of think of him as an ultra runner, but I guess he does a lot of skiing, and he's also done some record ascents of Everest relatively recently, and some other things like that. But anyway, he's a phenomenal kind of mountain runner and endurance athlete. And I don't know, it's, I mean, he's not a writer, let's say, but so, and being a sort of Catalan, I spent quite a lot of time in Catalonia, and he's quite effusive and descriptive, and kind of is given to these sort of flights of slightly poetic fancy about the mountains and his connection with the mountains and all this sort of thing. But so I've been skipping a couple of paragraphs, I admit, here and there. But yeah, just reading about what, like, for example, he did a traverse of the Pyrenees, which I've also done part of that route on foot, not running. But he did it in 8 days, and just reading about how on earth a person could, it's 800 kilometers, so 500 miles, and mountains, like serious mountains, how a person can do that. I mean, I went for a run this morning. I've been running every day so far this week, which is unusual for me. I'm normally like 4 or 5 a week at most. And 3 or 4 days of running every day, and I'm already like, I feel a bit stiff. I've ran like 6 miles or whatever. This guy somehow gets up day after day going, yeah, I'm going to do another 65 miles today, and somehow eat and not get injured. And anyway, so it's kind of amazing. It blows me away how almost anything you can sort of think of or describe, somebody's not only kind of doing it really well, but doing it on a scale or a level or at a speed or whatever that's totally incomprehensible. Not just like, wow, that's amazing, but like I can't even understand how that's possible.
I find that these things are especially shocking if you try running in those kinds of mountains. It's just unbelievable. Like I'm out after a few miles. I'm basically slowed to a jog, or well, to a slow walk, and I just don't understand how actually so many people can just keep running forever.
Yeah, for hours and hours and hours. And yeah, it's pretty cool. Humans are awesome, I guess.
Although Killian might be from a different planet or something.
Yeah, I mean, one of his, in that Trans-Pyrenean thing, one of his coaches said, you know, he's running with buddies often who are doing shorter segments of the race, and you know, their heart rates are what most people's heart rates would be at when they've been running all day, kind of, you know, 130, 140, 150. Killian's is 80. You know, so I mean, he's clearly biomechanically unusual, which I guess these people always are, you know, exceptional in some way. But yeah, remarkable. So there you go. Awesome. It's called Run or Die. So yeah. If I'm not here next week, that's what's happened.
Yes, indeed.
What are you reading?
I'm reading Democracy in America by you have a good French accent, Matt. Pronounce that name.
Where is it?
It's in the show notes. Aren't you in there?
Alexis de Tocqueville.
It was written in 1830.
Oh,
in his adventures to the United States. I was thinking last week about why democracy exists at all and exists the way it does in the United States. And I couldn't come up with a good answer, so I wanted to read something from the pre-Civil War era as an examination, an outsider's examination. I've just started, and it's fascinating. So
it is. It sounds unreadable.
No, it really is. It really is fascinating. But it's very long. I think it's 1,200 pages or something. So I'll report back to you next week when I'm 1/4 of the way through or something.
Does it have any pictures?
Not yet.
Okay, so there's no way I could read that book.
Before we sign off today, I wanted to mention that Houston, Galveston, Corpus Christi, many of the coastal towns in Texas get really hammered by Hurricane Harvey. And if you're looking for a way to help out, you can donate to various organizations. And also, I've put a link at the bottom of the show notes today where you can find some volunteering efforts going on that you can help out with. Zoltan, thanks for joining us on the show. It's awesome.
Thank you very much for having me.
Cheers, Zoltan.
Hope to see you back sometime. And I would love to learn a little bit more about the meandering channel modeling. Should we expect any of this stuff to go open source?
Hopefully, yes. It will take some time, but partly because it needs a lot of cleaning and before it goes public. But yes,
cool.
In the long term, yes.
Cool. I look forward to it. And hopefully we can have you back to talk about it some more. Guys, we will see you next week on Undersampled Radio.
Bye. Bye, everyone.
Bye.